Okay. The keynote speaker of our first report is Yibin Xu, Dr. Yibin Xu from National Institute of Material Science, Japan. Her report is devoted to construction of integrated materials data system for data-driven materials. Please, Yibin.
Thank you very much, Professor Kiseleva. So I will share my slide. Can you see my slide?
Okay, Yibin.
Okay, thank you very much. And many thanks for the organization committee for giving me this chance to talk at this great conference. And today I'm going to introduce some of our activities about materials data platform construction and data-driven materials research. Okay, why? Oh, sorry, I can't move my slide. Okay, so here this is my colleagues who contributed to this work. In our team, there are some members are material scientists, and some are computer experts, and some are data curators. I always believe that the collaboration between the experts in different fields is essential for getting success in this new technology field. And then today my talk, at first I will give a brief introduction to NIMS materials database. Then I will introduce materials informatics projects at MI2I. And finally, I would like to discuss some issues about materials database in big data era. So actually, the history of NIMS materials database can be traced back to 1995. At that time, Japan Science and Technology Agency, JST, started to develop some materials database. For example, database for alloy, for polymers, and some for diffusion. And at the same time, National Research Institutes for Metals, which is the predecessor organization of NIMS, published structured materials data sheets for creep, corrosion, fatigue, and also developed some database like CCT diagram and superconductor. NIMS was established in 2001, and in 2002, the GST's database has transferred to NIMS. And that from then, NIMS started to construct a new database, materials database system, MATNAVI. This is the top page of current MATNAVI. We have many versions, but this is the current version. And MATNAVI is open for internet access for free. And some important databases, including Polyinfo, which is a database for polymer, and Atomwork, it's a database for inorganic materials. And we also have a database for diffusion, for superconductor, and these data are all extracted from literatures. There are also some computational database for phase diagram and for electronic structures. And we also have some experimental database for metals, CCT diagrams, and some of physical properties. And from 2018, we started our first commercial database service as inorganic materials database, Atomwork Advance. I can't focus. Atomwork Advance, the data was developed under the construction, under collaboration between NIMS and MPDS, a Swiss company. The data contains the phase diagram, crystal structure, and the properties for inorganic materials, which extracted from about 160,000 publications. And all these data are interlinked at the level of substance, even they are from different papers. And here, this is the number of data entry of current atom work advance. The data was annually updated. And since 2020, NIMS started a new database platform, DIAS. This is the top page of DIAS. Matnavi is only a part of it. And also we have some other data service, for example, materials data repository, and it's also open for internet access. And there are some other systems, some other systems just for internal use. For example, the data transfer tools from the equipment to server, or the text data mining platform, and so on. And gradually, we are open this service to the people outside NIMS. Sorry, I can't move. Okay, so and also we have many database systems is under construction in order to contain the data generated by national organizations and national projects. And in the future, NIMS is going to become a data center of all Japan's materials data. And there are many national projects are using Matnavi data. And here I'm going to introduce one of them. It's a Material Research by Information Integration Initiative, abbreviated as MI2I. This project contains from 2015 to 2020. It's a 5-year project, and it's managed by Japan Science and Technology Agency, JST, and NIMS. And the researchers are from all of Japan. And here are the project leader and the group leaders. And all the project include 3-layer structure. At the bottom is a data platform group. And this group is in charge of data service, data management, and data generation. And in the middle layer, there are 4 groups which are responsible for development of elemental technologies. For example, machine learning tools, and topological analysis tools, and the materials feature selection, and materials exploration. And on the top, there are 3 groups targeting for the practical materials for batteries and magnetic and thermal management material. And in this project, I was in charge of 2 groups, the data platform group and the thermal management material group. And we, in this project, we developed an ML2I data platform system. And this system is considered as the prototype of the current NIMS DIAS data platform. And here is the structure of the system, and it's composed of a computing cluster, which is suitable for middle-scale simulation, and MI2 Cloud, which we can provide virtual machine service for the project member. And we have storage about 200 terabytes, and there is a database server and web server, which provides the web service of API to access database and some web applications of machine learning. And this system was built inside NIMS network. The project members and the consortium members, as for usually from industry, they can access this system through VPN from all of the Japan. So here, this is our API service for database. In Matnavi, Matnavi only can be browsed by on the web browser. A user cannot download a large amount of data. But in this in MSQL data platform, we have developed API for all of the NIMS database, and the researchers can send HTTP requests to the server and get the response in the JSON format. In this way, the user can download all of the data of Matnavi. And furthermore, because some materials researchers, they are not good at programming, not at coding. For such kind of user, we also provide a GUI for using the API. This GUI was developed based on Orange. We have prepared some widget, so user can just select a widget and link them together, so they can download all of the data without writing any code. And for the user who like to use Python, we provide environment Jupyter Cloud and also with some sample codes. For example, the user can use the sample codes to download the data from using Web API and also do some simple data analysis, like plotting the data or do some machine learning. For the cluster computing, it is suitable for middle-scaled high throughput computation. And the most common use is to, for example, download the crystal structure from Atomwork Advanced as a zip file and use the zip file, send the zip file for first principle calculation and obtain the data like electronic structure. For this purpose, we also provide a toolkit named Toast. It can help the user to do high throughput first principle calculation. The Toast will parse a zip file and generate the files for first principle calculation and launch the first principle computation engine and get the output files and passing the data and do the post-processing. Finally, the user can get the data of relaxed structures as a zip file and electronic structures and metadata and files for visualization results. And Toast can work together with the VASP, Quantum Espresso, and ABINET. Oh, sorry. And also we have provide a virtual machine service. The virtual machine service allows the user to build a private space on the cloud. And this user can use all the resources we provided on the platform, the data, the tools, and they can combine with their own data and tools, and without worrying about some others will know his data or know what he's doing. And because especially for some members from industry, they would like to keep secret of their own data and their research work. So especially we provide such a private service for them. And also for the user with little experience for machine learning, we provide some simple web applications for this user to experience the machine learning. And for example, this is a system to predict the possibility of compound formation. If the user just input a chemical system and the application can predict the possibility of the compound formation. And with the random forest and with the descriptors like the atomic number, periodic number, and others. And here's another web application is to help user predict specific heat from experimental data by machine learning and also by physical laws, Neumann-Kopp's law. And finally, the system will show the experimental data and the machine learning prediction together with the Neumann-Kopp rules prediction. And also it can calculate the Debye temperature from each of these three curves. And so now I'm just going to introduce some results of our data-driven materials research to development of an inorganic thermal insulating material leveraging interfacial thermal resistance. And at first, what is interfacial thermal resistance? That's what when we have two materials combined together, there will be an interface in between. And when heat flux past this interface, the energy carrier, phonon or electrons, will be reflected or scattered. So only a part of them can pass through it. So it causes an extra thermal resistance. We call it interfacial thermal resistance. And if we look at the temperature of this system, we can find a temperature jump at the interface. Then, how large is the ITR, interfacial thermal resistance? We can compare it with the SiO2 glass, the thermal resistance of Si2 glass with thickness of D. Then the ITR of solid surface can equivalent to a D ranged from several nanometers to several hundred nanometers. So this gives us a hint that if we can design an interface with very high ITR, and we make nanomaterials, including many such kind of interfaces, we have chance to develop material with very low thermal conductivity. So this is our concept. But the point here is we have to design an interface with with high thermal resistance. And in the past 15 years, we have studied the factors which were affecting ITR by the experiment, physical models, and molecular dynamic simulation. And we find the ITR is a very complicated phenomenon, and some properties, of course, the property of the materials, like the Debye temperature and acoustic velocity, will affect it seriously. And also the mismatch between these properties of the two materials will have great effect on it. And besides that, it is also affected by the atomic imperfection, like vacancy and atomic mix exchange at the interface. And also it depends on many materials processing, like the contact area, crystalline state, the grain size, and the chemical bonding. They will also affect the ITR obviously. So it is a very complicated phenomena, and physical models usually can only consider a part of these factors. So it's difficult to give a prediction of ITR by physical models. Here I show the comparison between a physical model's prediction with the experimental value. And DMM is the most commonly used physical model for predicting ITR. If we took the DMM prediction as the vertical axis and experimental value in the horizontal axis, we can see that the accuracy actually is not very high. So there are a large deviation between them. So we feel that it's difficult to have a physical model to predict ITR. Then we try to use machine learning model to predict the ITR. So we started from collecting experimental data from papers, and actually we collect paper from 86 papers, data from existing papers, which include 456 samples, and they are composed by 54 substances. And finally, totally we have more than 1,300 data points. And when we show here, the red point shows the metameter interface, and the blue point shows the others. And because of the metameter interface, the energy carrier electron. But for the other case, phonon is the main energy carrier. As we can see clearly, the electron has much lower thermal interfacial thermal resistance than phonon. But in this case, in this study, we want to find the interface with high thermal resistance. So that's why actually we use only this blue data. The next is how to select descriptors of ITR. And according to our experience, we know that the property of the material is important descriptor. And the next slide, I will explain how we select the property descriptors. and also the compound descriptor, which shows how easy a new compound will form, the formation of new compound at the interface. That's also important descriptors. In this case, we selected atomic coordinates, atomic mass, electronic negativity, ion contact potential, and binding energy as the compound descriptor. And also the material process descriptor are also important. Unfortunately, when we collect data from papers, we can seldom find common descriptors for different synthesis method. And finally, we only find two, as film thickness and interlayer. And for the property descriptor selection, there are many properties related to heat transport. And some of them are difficult to obtain. Some of the data are difficult to obtain, or even we can obtain, but it has large uncertainty. It's quite a large deviation between different papers. And so fortunately, these properties are not totally independent. In this graph, we show the correlations between these properties. We can see some property, they do have a very high correlation. For example, the heat temperature, Debye temperature, and the sound of speed, and the acoustic velocity. If we plot them together, we can see a very clear linear relationship. And some others, like thermoconductivity and the melting point, they have some weaker but still obvious correlation. And actually, if two property with strong correlations, that means the physical and the chemical factors dominating them are quite similar. So as a descriptor, we don't need to use both of them. We think just choose one, and then they can as a representative of them. So in this case, with this method, we try to select the properties with sufficient and high quality data. And finally, we select the heat capacity, melting point, density, and unit cell volume as our property descriptor. Then the next question is, which machine learning model should we use? And actually, we tried maybe 6 or 7 different machine learning models we can try. And from them, the first step is we compare the statistical accuracy of this model. And then we find 3 models with high statistical accuracy: AirSboost, support vector machine, and the Gaussian regression processing, Gaussian process regression. Then if we just look at this value, our square value, for all of these 3 methods, they can give a satisfied high value. And here is the comparison between the AirSboost prediction and experimental value. We can see it's much more accurate than the physical model. But however, that's just from statistical accuracy, we cannot distinguish which model will be better. So the next step is we try to analyze the importance of the descriptors for these 3 models. And the x-axis, we list up all the descriptors we give for machine learning, and the color shows importance of the descriptor. And we can see they have different patterns. That means for these 3 models, they think they have different, the importance of descriptors are different. Especially the AirSboost, it has quite a different pattern with SVG and GPR. And so that we can understand, even we give them the same data, actually they treat them with different importance. And with the training data and training data set, even they can get very high, with similar accuracy. But when they're predicting the new interface, it's not surprising that they will give different predictions. So actually, we try to predict the ITR for the 80,000 material combinations, and each model recommend the top 100 high ITR interface. And we can see that only 3 of them, or 3 of the interface are recommended by both all of these 3 methods. And there are another 23 interface are recommended by 2 models. since we would like to have the view from different point of view, actually we just take this overlap part, and this is the multi-dimensional scale of this 25 interface. This orange one are the three interfaces recommended by the three models. But when we consider of material development, we have to think about the easiness of synthesis and stability of the interface and environmental hazard, cost, and the others. And finally, actually, we select the bismuth silicon as the interface for experimental verification. The first we do is to we build a single bismuth silicon interface by deposit bismuth film on the silicon wafer and measure the interfacial semiconductor resistance of this single interface. And here is our experimental result in comparison with the machine learning prediction. And the SVT and the GPR, they give a very similar prediction. And unfortunately, our result is support the Aries boost model. So actually, that means that just the statistical accuracy may be not enough to judge the reliability of the machine learning model. And then the next, we try to make a nanostructured material with bismuth and silicon. And we use our combinatorial sputtering equipment. And we developed, we synthesized the composite material of silicon and bismuth under different conditions. So the X-ray diffraction, X-ray analysis shows they are these material are composed of amorphous silicon as matrix and the crystalline bismuth as the particles dispersed inside it. And depends on our experimental condition, we can have different grain size and different orientations of bismuth. Then we measure the thermal conductivity of this material. And here, the green triangle are our result, and the others are the thermal conductivity we reported by the papers, previous work. And we can see for the inorganic nano composite, we get a very low value. It's lower than the previous work. And actually, our data, the lowest data, thermal conductivity 0.16, it's quite similar to polymer. And it's not usually polymers usually are considered as have very lower thermal conductivity than inorganic material, but our inorganic nano material composite, we can obtain the thermal conductivity very similar to a polymer. So with this work, we know that machine learning is helpful to model complicated material phenomena such as interface. And it was helpful to decrease exhaustive experiments and computation. However, the data is the bottleneck. And in this graph, I showed the availability of property data for different substances. And this statistic was done over about 500 properties of 115,000 substances based on Atomwork Advance. So we can see the property with the highest availability is magnetic susceptibility. Is available for 7% substance. And electrical resistivity is only available for 5% substance, and heat capacity for 3%. Bulk modulus and thermal conductivity is only available for 1% substance. So we know actually the property data are we have very, very little property data for the substance we know. And also this graph I showed the trade-off between the database scale and applicability of material. And usually for the compound, we have the largest database. Usually they can be 1 billion scale, and in a billion scale. And for single crystal, we have database with scale of 1 million scale. But for the most applicable materials, such as multi-phase and composite material, the database scale is much small, usually only several thousand or 10,000. So all this situation makes the data availability, it's quite difficult to obtain sufficient data for the data-driven materials research. Also, the machine learning model, the reliability is also a problem. And we think the machine learning today is a baby without any domain knowledge. The baby doesn't know about material, about theory, about physics, about chemistry. It's just a baby. He judge everything according to the data we give it. And it will make models anyhow, but some of them are good, some of them might be not good. Then how to judge if this model are good or not? Of course, statistical accuracy provides us a very important criteria to judge a good model or not. But it is not enough. As I said, we have 3 models, both have very high statistical accuracy, but when they predict new substance, they give totally different result. So actually, scientific insights into this model are still necessary to evaluate the reliability and understand the limitation of the machine learning model. And then I would like to talk about something about materials database in the big data era. So at first, what's the difference between a big database and big data? And if we have a big database, do we think we have a big data? Of course, it is no. The answer is no, because a database usually with a specific structure, that means the database will focus on some specific type of data for specific type of materials or specific type of properties, because they are structured. But for the big data, materials big data, because the purpose of materials big data is finally to design a new material and to find the correlation between the processing, structure, and property. So actually, we need to integrate all those data. We need to extract the data from different databases, integrate them, and to make them a comprehensive data set in order to be processed by machine learning and the other AI method. So data integration is the most important issue for the materials big data. Then what do we need to integrate materials big data? Of course, maybe the common data format, that's always a common topic. There are many research work and report about that. But actually today, I would like to say that material identification is an even more essential problem. And why? That is because for one material, there has various aspects, the composition, crystal structure, microstructure, and property, performance, and processing conditions. But we have little chance to obtain all those data from one data resource. Because researchers, they are specific in a field. For example, crystal structure, they just measure crystal structure. Someone experts for electrical property, they only report electrical property. But when we need all of those data for one material, we have to combine this data from different resources. So in this case, material identification becomes very important. We have to judge if they are same material, or even they are not same, how similar they are, and at which level we can treat them as same. So actually, material identification can be divided at 4 different levels. One is chemical system, that is what element composed included in this material. Another next one is compound, that include chemical composition. And the third level is the substance level, or we can call phase level. We know not only the compound, we also know its crystal structure or its state. And the fourth level, the highest level, is material. But unfortunately, we have little chance to obtain two exactly same material if they are provided by different resources. Because depending on the synthesis conditions, that usually they can have very little difference in the little or larger difference in the microstructure. So they cannot get the totally exactly same property material from two different resources. And so in this case, in many databases, we identify the material at the compound level or at the substance level. But the compound level is rather easier. Unfortunately, many properties and performance is strongly dependent on crystal structure. So I would like to say that the compound level identification may be not enough, but at the substance level, identification would be better. Then let's look at the descriptors of compound and substance. For compound, the most commonly used descriptor are chemical formula. We write in this way, or if it has some atomic replacement, it can be also written in this way. But for crystal structure, it's much more complicated. There are different ways for describe crystal structure, and crystal system is the most basic way. It's a cubic system or hexagonal, and that's the most basic way to identify crystal structure. And the Bravia lattice is a crystal system plus the centering type, and that usually we call it BCC model, is BCC structure or FCC structure. That is actually it's referred to Bravia lattice. And Pearson symbol is defined by Bravia lattice plus number of atoms in unit cell. And space group, which is the most commonly used descriptor for computational people or for the crystal structure people. And structure type, it's also a way. But now even in atom work, we know there are already more than 20,000 different structure types. To assign a structure type of a material is not easy. Then we can see the effect of the descriptors of the crystal structure. Here I use also the number of atom works. And for the unary system, that means the system, the material is composed by only one type of element. And for the binary system, which is composed of two elements. And the number, if we identify the substance by chemical formula plus Pearson symbol plus space group and plus structure type, totally we have 648 substance for unary system and 15,264 substance for binary. But if we just look at the chemical formula, we can find only 116 substance for unary, and which is 18 part of the unary system, and only 11,248 substance for binary, which is 74% of the substance. So it's obviously not enough. And if we include the chemical system, a crystal system as a descriptor, we can identify the 52% and 86% substance respectively. And if we use Bravia lattice, this number increased to 75% and 92%. And if we use space group, it becomes 84% and 92%. And use Pearson symbols, it's 92 and 95. And of course, if we use the combination of them or use crystal structure, we can get higher identification. So basically, we think we need the descriptors we need to describe a substance is chemical formula plus at least one of the crystal descriptors between space group, Pearson symbol, and structure type. But unfortunately, for many researchers, especially experimental researchers, they are not used to use space group. They would like to describe their material by the crystal system or Bravia lattice. So to fill this gap between this, actually we are making a dictionary of substance and based on atomic advance. In this case, we described every substance by its chemical formula and the crystal structure. For the chemical formula part, we use the coefficient. It's not a specific number. It can cover a range of the number, which can be used for the substance with atomic replacement. And also for the crystal structure part, we give the space group, Pearson symbol, structure type, and other notations if they have. If the user doesn't only know the crystal system or Bravia lattice, it still have chance to identify the substance from the Pearson symbol. For example, the T means the tetragonal, and this Ti means the tetragonal crystal system with body-centered structure. So in this case, for the material people, they can easily identify a substance using the descriptors we recommended. And now with this substance dictionary, we are possible to link the materials database with the substance database. Materials database usually we usually include the items as chemical composition, synthesis process, phase composition, nanomicrostructure, property, performance. And for substance jurisdiction database, we specify compound and crystal structure. And also there are some first principle database. They can, like electronic structure and the phono structure, they can use the crystal structure from the substance database. Now, when we use this substance dictionary, we make easier for the database developer to link the phase composition, each phase of the material to a corresponding substance in the substance database. So that's possible. Enable us to obtain all the data from different databases. And here actually it's a database we are under construction. And this we are constructing a database for battery materials from the literature, published papers. And in NIMS, we have a text data mining platform, which can provide more than 1.5 million articles from various publishers. And what we are going to do is at first we use natural language processing to process this material, this literature. And in this case, we can find an overview of the research in this field and analyze the tendency of the research. And also with combination of natural language processing and data curator, we can select some papers with high importance and high value and very high valuable data. And this data will be read by data curators and extracts the data and build some materials database. For example, electrode materials database or solid electrolyte material database. But all these databases will link to the atomic advance, which can provide the crystal structure and the property data of the substance. And behind it, it's also linked to the electronic structure and the phonoproperty structure. And so this system is just under development. As conclusion of my talk, data integrability is required for materials database in big data era. For this purpose, standardization of descriptors are necessary. But standardization of descriptors at the materials level is difficult, but at the substance level is realistic and practical. And linking materials database to substance databases can provide us comprehensive and add valued information for data-driven materials research. And thanks for our funding agency for this project. And thank you very much for attention. I'll be happy to answer any questions. Thank you very much.
Thank you, Dr. Xu, for very interesting report. It is experience of development of very good databases in the domain of inorganic chemistry and material science. And one my Question. Your institute is the largest developer and distributor of substance and materials properties databases. We have integrated your Atomwork database with our databases. Are you considering the prospect for integrating your another databases with other information system developed in the world and in our country?
Yeah, surely. For myself, I always believe one organization or one country cannot cover all the materials data, and it is absolutely necessary to have a collaboration between different organizations and different countries. And the problem is actually, as you know, there are some, each database have their different open policy and different security policies. And actually, also we are struggling for that. When we develop, every time when we develop the new database, it depends. It's so much things we have to obey. Especially the information security. And for example, right now, when we develop new database, that we have to prepare for some attacks for the server, and also we have to prepare for if someone they download illegally a large amount of data and build their own database. So it's always struggling. I know that we still have many problems, but I hope we can resolve it one by one to finally get some. We can have a system which is convenient for all the researchers of the world.
Thank you, Yibin. We have now the problems with your new security model, but I hope that we solve this problem in future.
I know, yes, I know, I noticed that. I'm sorry about that, but it's very, very complicated. Maybe we can keep on talking about that.
Okay, next questions.
Hi.
Oh, thank you, Yibin, for very, very, very interesting report. Thank you.
Thank you.
I transfer my right to Dr. Stupnikov. Please, Sergey Alexandrovich.
Yeah, I'm here. But actually, as I understand, do we have some more questions on our excellent keynote talk? Okay. So Dr. Psu, thanks a lot again.
Thank you,
Thank you very much.
Okay.
Thank you.
And, actually, the session C1 of our conference will start in about half an hour. So I welcome you to the next session of our conference.